Somewhere in China, people are walking across a grassy hill jogging, sitting, enjoying the view. What they don't realize is that 30,000 screaming fans are packed into a stadium directly beneath their feet. You heard that right, an entire sports arena, buried underground, invisible from the surface. This isn't science fiction. This is real engineering, and it's happening right now. And once you understand what it actually took to pull this off, the excavation, the structure, the sheer scale of the problem engineers had to solve, you'll never look at a park the same way again. What is an underground stadium? Imagine being told you need to build a stadium not on top of the ground, but inside it. No towering walls rising above the skyline. No massive concrete bowl visible from miles away. Just a hill, a park, and 30,000 seats hidden beneath the surface. That is exactly what underground stadium design demands, and it is one of the most radical shifts in sports architecture happening anywhere in the world right now. An underground stadium is exactly what it sounds like. A sports venue built partially or entirely below ground level, embedded into the earth so that the structure disappears into the surrounding landscape. Instead of a building that sits on top of a site, the stadium becomes part of the terrain itself. The seating bowl is excavated downward. The roof, rather than being a ceiling you look up at, becomes a surface you walk across. But here is what makes this so much harder than it sounds. A standard stadium is already one of the most structurally complex buildings you can construct. Now, take that same challenge, the massive foundations, the enormous roof spans, the crowd loads, the safety requirements, and push the entire thing underground. Suddenly, you are not just building a stadium. You are fighting against soil pressure, groundwater, limited airflow, and the weight of an entire landscape sitting on top of your structure. Every problem that comes with building a stadium gets amplified the moment you bury it. So why would anyone choose to do this? Because cities are running out of space. Urban density is climbing. Green space is disappearing. And communities are no longer willing to sacrifice entire neighborhoods just to accommodate a stadium that sits empty 300 days a year. Underground design offers something extraordinary, a sports venue that gives back more than it takes. The park above becomes public land. The visual bulk disappears. The city breathes. This is not just an architectural trend. It is a fundamental rethinking of what a stadium can be, and China is building the blueprint. And the project that started it all begins in a city most people outside China have never heard of. Quzhou Sports Park, the vision. The city of Quzhou sits in Zhejiang province in eastern China. Not a megacity, not a global landmark, just a mid-sized urban center looking for an identity. What it got instead was one of the most talked about stadium designs on the planet. And it started with a single, almost impossible brief. Build a sports park that feels like it was always part of the landscape. The firm handed that brief was MAD Architects, led by Chinese architect Ma Yansong. MAD had already built a reputation for designs that blurred the line between architecture and nature, buildings that looked like mountains, towers that curved like wind. But Quzhou was different. This was not about one building making a statement. This was about making an entire sports complex vanish. Ma Yansong's concept was rooted in a philosophy he calls Shanshui City, a vision of urban environments where natural landforms and built infrastructure merge so completely that you cannot tell where one ends and the other begins. At Quzhou, that philosophy became literal. The stadium bowl would be carved into an artificial hill. The roof would not be a roof at all. It would be the hill itself, planted with grass, laced with walking paths, and open to the public every single day. But the moment MAD presented this vision, the engineering team faced a reality check that stopped everyone in the room. Because designing a stadium that disappears into the earth is one thing. Actually building it is something else entirely. The hill above the stadium would need to carry soil deep enough to sustain real vegetation, not decorative patches of grass, but an actual living landscape. That soil alone, when saturated with rainwater, would weigh tens of thousands of tons, pressing down on the roof structure below. And underneath that roof, 30,000 people would be sitting in a stadium bowl that had been carved out of the ground like an open wound in the earth. The vision was breathtaking. The engineering problem it created was almost paralyzing. But this was just the beginning of what the team would have to solve. The excavation challenge. Before a single seat could be installed, before the roof could be designed, before any of the engineering solutions could be applied, someone had to dig the hole. And the hole required for a 30,000-seat stadium is not something you can fully prepare yourself for until you are standing at the edge of it. The excavation at Quzhou required removing millions of cubic feet of earth from a site that needed to remain stable throughout the entire process. To put that in perspective, you are not just digging a basement. You are carving out a void large enough to fit multiple city blocks, going deep enough that the walls of the excavation rise higher than a 4-story building on every side. And you have to do it without the surrounding ground collapsing inward. The process could not happen all at once. Staged excavation was the only viable approach, removing earth in carefully calculated sequences, reinforcing each level before digging deeper, and continuously monitoring the surrounding soil for any sign of movement. One miscalculation in the sequencing and the walls of the pit could shift. The ground surrounding the site could crack. Neighboring infrastructure could be compromised. Then came the problem that every excavation team in this region dreads. The deeper you dig in eastern China's soil profile, the more unpredictable the geology becomes. Layers of soft alluvial soil alternate with harder strata in ways that standard excavation equipment is not designed to handle cleanly. The machinery had to be adjusted, the digging sequences had to be recalculated, and the engineering team had to make real-time decisions about how to proceed without losing the stability they had already fought to establish. And the clock was never not ticking. Every day the excavation stayed open without being reinforced was a day the surrounding ground was under stress. Weather events, groundwater fluctuations, even vibration from construction equipment, all of it applied pressure to a pit that was already operating at the edge of what the soil could tolerate. The hole eventually reached its final depth. The team had done it, but what they found waiting for them at the bottom of that excavation made the digging look straightforward. Retaining walls and structural reinforcement. Once the excavation reached its final depth, the real structural battle began. Because an open hole in the ground, no matter how carefully dug, is inherently unstable. The earth surrounding it wants to move. Gravity, soil pressure, and groundwater are all constantly pushing inward. And without a system powerful enough to resist that force permanently, the walls of the excavation will eventually fail. At Quzhou, the retaining wall system was not just a construction phase measure. It was a permanent structural component that the stadium would depend on for its entire lifespan. The primary solution was reinforced concrete diaphragm walls, massive panels cast directly into the earth along the perimeter of the excavation before the digging even reached full depth. These walls act like a buried fortress, holding back the lateral pressure of thousands of tons of surrounding soil. Each panel had to be precisely placed, precisely reinforced, and precisely connected to the panels beside it, because a single weak joint in the system would become the point where everything eventually moved. But diaphragm walls alone were not enough. The lateral pressure on a below-grade structure of this scale is not static. It shifts with moisture content, with temperature changes, with seasonal ground movement. To counter this, engineers combined the diaphragm walls with soil nailing and ground anchoring systems that reached deep into the stable earth beyond the excavation boundary, tying the walls back against the pressure, trying to push them inward. Then came the problem of differential settlement, the risk that different sections of the stadium foundation would sink at different rates over time. In a surface building, minor settlement can often be tolerated or corrected. In an underground stadium with a massive green roof sitting on top of it, uneven settlement would crack the waterproofing, compromise the drainage systems, and ultimately threaten the structural integrity of the entire assembly. The foundation design had to be extraordinarily precise. Deep pile foundations were driven into the bedrock below the soft upper soil layers, distributing the load in a way that minimized any differential movement between one section and another. The walls held, the foundations were set. But the next enemy was one you could not see, could not touch, and could not stop. It was already there, rising from below. Groundwater management. Water does not care about your construction schedule. It does not care about your engineering budget or your architectural vision. It finds every crack, exploits every weakness, and applies pressure in directions that no surface building ever has to account for. For an underground stadium, groundwater is not just a construction nuisance, it is a permanent structural threat that has to be defeated before a single spectator ever takes their seat. At Quzhou, the groundwater table in the surrounding soil sat at a level that put it dangerously close to the base of the excavation. During the construction phase, the team deployed an aggressive dewatering strategy, a network of deep wells and pressure relief systems installed around the perimeter of the site to continuously draw water away from the excavation zone. Without this system running around the clock, the bottom of the pit would have become a swamp. The weight of the construction equipment alone would have driven machinery into saturated soil that could no longer support it. But dewatering during construction is only half the battle. Once the stadium was built and the pumps were switched off, the groundwater would begin migrating back. And now it would be pressing against a permanent concrete structure instead of open earth. That pressure, called hydrostatic uplift, is one of the most dangerous forces an underground structure can face. In extreme cases, it is powerful enough to push an entire building upward out of the ground, cracking foundations and rupturing waterproofing systems in the process. To counter this, engineers installed a permanent under-drainage system beneath the stadium floor, a carefully designed network of drainage channels and pressure relief points that manage water accumulation below the structure and prevent uplift. Pressure from building to critical levels. Above that, multiple layers of waterproofing membrane were applied to every below-grade concrete surface, creating a barrier that water cannot penetrate even under sustained hydrostatic pressure. The system works, but it has to keep working every single day, in every season, through every weather event, for the entire life of the building. The water had been controlled. The structure was sealed. Now the team faced the challenge that would define the entire project, and the one that no one had ever attempted at this scale before. The roof as a public park. This is the moment where the engineering story stops being about what happens underground and becomes about something far more ambitious. Because the roof of Quzhou Sports Park Stadium is not a roof in any conventional sense. It is a public park, a living, breathing landscape that sits directly on top of a 30,000-seat arena, and every single element of it has to be engineered to carry loads that would challenge a bridge designer. The structural framework spanning the stadium opening is a massive steel assembly, engineered to bridge a void that stretches hundreds of feet across without a single interior column interrupting the sightlines below. The geometry of that steel framework had to be calculated with extraordinary precision, not just to carry its own weight, but to support the full layered system of the green roof above it, including drainage infrastructure, a growing medium deep enough to sustain real vegetation, and the dynamic load of thousands of people walking, running, and gathering on the surface simultaneously. That soil load alone is staggering. When the growing medium is fully saturated after heavy rainfall, the weight pressing down on the roof structure multiplies dramatically. Engineers had to design for the worst-case scenario the heaviest possible soil saturation combined with maximum crowd density on the park surface, and ensure the steel framework could absorb all of it without deflecting, beyond acceptable limits. But the layered construction of the green roof introduced its own complications. Below the soil sits a drainage layer that manages water movement across the roof surface. Below that sits a waterproofing membrane that protects the structural deck from moisture infiltration. Below that sits the steel deck itself, connected to the primary structural framework. Every layer had to perform its function independently, while also working in concert with every other layer, and a failure in any one of them would compromise everything above and below it. The result is a roof that behaves like a park, performs like a bridge, and looks like a hillside. And the people walking across it have no idea what is holding them up. But keeping the structure standing was only part of the challenge. What happens to the air inside a stadium that is buried in the ground? Ventilation and environmental systems. A stadium buried underground has a problem that no open-air venue ever faces. The air inside it has nowhere to go on its own. There is no prevailing wind sweeping through the stands. There is no natural convection pulling heat upward and away from the crowd. There is just a sealed bowl, 30,000 people generating body heat, and an atmosphere that will become unbreathable, remarkably fast, without an aggressive mechanical intervention. The ventilation infrastructure at Quzhou had to be designed from scratch as a purpose-built system, because no standard stadium ventilation playbook accounts for a venue that is effectively sealed beneath a landscape. Fresh air supply ducts had to be routed through the earth surrounding the stadium, carefully coordinated with the structural and waterproofing systems to ensure penetrations did not compromise the building envelope. Exhaust pathways had to be engineered to remove heat and carbon dioxide efficiently enough to maintain air quality across the full seating bowl during peak occupancy. The thermal challenge compounded this problem. Underground spaces do not shed heat the way surface buildings do. The earth surrounding the stadium acts as an insulator, which is useful in winter but becomes a serious liability during summer events when the combination of crowd heat, lighting loads, and trapped air can push interior temperatures to dangerous levels without adequate mechanical cooling capacity. Acoustic behavior added another layer of complexity. Sound in a partially enclosed underground bowl behaves differently than in an open-air stadium. Reflections from the retaining walls and the roof structure above create echo patterns that would make crowd noise and public address systems almost unintelligible without deliberate acoustic treatment integrated into the pans. Interior surfaces. The engineers solved each of these problems. The air moves, the temperature is controlled, the sound is managed, but none of it is visible to anyone sitting in those seats, which is precisely the point. The structure breathes, but the ground it sits in can shake, and that required a completely different category of engineering thinking. Seismic engineering underground. China sits across some of the most seismically active terrain on Earth. The same tectonic forces that shape the mountain ranges of central and western China send tremors through the ground across the entire country. And no major structure anywhere in China gets built without a serious reckoning with what an earthquake will do to it. For an underground stadium, that reckoning is more complicated than it is for any surface building. Here is what most people do not realize about underground structures and earthquakes. Above-ground buildings sway. They are designed to move with seismic energy to flex, absorb, and dissipate the ground motion before it can tear the structure apart. An underground structure cannot sway freely the same way. It is surrounded by earth on all sides, and when the ground moves during a seismic event, the structure moves with it. The soil itself becomes part of the dynamic system, and the forces transmitted to the building are fundamentally different in character from what a surface structure experiences. At Quzhou, the foundation system had to account for this reality. Deep pile foundations were driven through the soft upper soil layers and anchored into the stable bedrock below, not just to manage settlement, but to ensure that seismic energy was transmitted to the structure through a controlled, predictable load path, rather than through the unpredictable behavior of soft soil layers above. The connection between the pile foundations and the stadium structure was detailed to allow a controlled degree of movement while maintaining the structural integrity of the retaining walls and the roof framework simultaneously. The retaining walls themselves required seismic detailing that went beyond their primary function of resisting lateral earth pressure. During an earthquake, that lateral pressure spikes dramatically as the surrounding soil accelerates. The wall reinforcement had to be designed to absorb those dynamic load spikes without cracking or separating from the foundation system below. Every weld, every connection, every joint in the steel roof framework above was designed with seismic load combinations in mind. The ground can move, the stadium is ready for it. And what all of this engineering ultimately made possible goes far beyond the stadium itself. Urban integration and landscape design. Step back from the structural details for a moment and look at what this stadium actually does to the city around it, because the engineering achievement at Quzhou is not just about building something underground. It is about what that decision gives back to the people who live there, and that is something most sports venues never even attempt. A conventional stadium of this scale would have consumed an enormous footprint of urban land and replaced it with a structure that generates activity on roughly 50 event days per year and sits as dead urban infrastructure for the other. 315. The visual bulk alone would have reshaped the surrounding neighborhoods, casting shadows, generating traffic and creating a barrier in the urban fabric that pedestrians route around rather than through. At Quzhou, none of that happened. The stadium disappeared into the earth, and in its place appeared a continuous public landscape, terraced gardens, walking paths, open green space that is available to the city every single day, regardless of whether there is an event happening below. The park surface connects seamlessly to the surrounding urban fabric, drawing pedestrian movement across it rather than around it. This is what architects mean when they talk about urban integration at the infrastructure scale. The stadium is not a building that sits in a park. The stadium is the ground that the park sits on. The boundary between sports venue and public space has been dissolved completely, and the city is richer for it in ways that go far beyond the event calendar. Ma Yansong's Shan Shui city philosophy found its fullest expression here. The artificial hill that contains the stadium reads as a natural landform from every direction. Visitors who have never heard of the stadium below walk across its roof without a second thought, because there is nothing about the landscape that signals infrastructure beneath their feet. The city gained a stadium and a park simultaneously. That is the promise of underground design, and Quzhou delivered on it completely. Stadiums that disappear. You have now seen everything it took. The excavation that carved a void large enough to swallow a city block. The retaining walls holding back thousands of tons of earth pressure every single second. The dewatering systems fighting groundwater that never stops trying to reclaim the space. The steel roof framework spanning hundreds of feet while carrying the weight of an entire living landscape above it. The ventilation infrastructure breathing life into a sealed underground bowl. The seismic foundations anchored into bedrock, ready for the ground to move. All of it invisible. All of it buried. All of it working in silence beneath a grassy hill where people walk their dogs and watch the sunset. This is what Quzhou Sports Park Stadium actually is. Not just a building, not just an engineering project. It is proof that the relationship between sports infrastructure and the city does not have to be adversarial, that a venue capable of hosting 30,000 screaming fans can exist in the same space as a quiet public park at the same time, without either one compromising the other. Ma Yansong and mad architects did not just design a stadium. They demonstrated a new principle that the most powerful thing architecture can do is disappear. That the greatest engineering achievement is not the structure you can see, but the one you cannot. That burying something this complex, this massive, and this demanding beneath a living landscape and making it look effortless is not a limitation of ambition. It is the highest expression of it. As cities grow denser, as urban land becomes more contested, as communities demand more from the infrastructure built in their neighborhoods, the underground stadium is not going to remain a novelty. It is going to become a model, and the engineers and architects who cracked this problem in a mid-sized city in Zhejiang province will have left a blueprint that changes how the world builds sports venues forever. Somewhere in Quzhou right now, someone is walking across that hill. They have no idea what is beneath them, and that is exactly the point.